Welcome to our NPTEL lectures on flexible SC transfer fax devices. We shall continue with our discussion on TSSC, followed by we will discuss about TCSC. We will try to close both this unit in today's half an hour's lecture. So, we have to deal with these two entities here now. So, let us go to the topic where we have left. So, we were discussing about TSSC. So, and the control internal control technique. In order to minimize the initial surge current in the valve and the corresponding circuit transient, the thyristor valve should be turned on or bypass only when capacitor voltage is 0. So, we have to see that and we require to do that. So, how to do that? With the prevailing DC offset, this requirement can cause a delay up to a full cycle, because you have seen that there is a DC offset will be there in case of this TCSC, which would set theoretically the limit for the attainable response time of the TCSC. So, there will be a delay till the voltage across these devices becomes 0. In principle, TCSC switching could be modulated to counteract the subsynchronous oscillation. So, we can damp out in such a way the current through the system in such a way that it will damp out the subsynchronous impedance. Therefore, pure TCSC scheme could not be used in a critical application where high degree of compensation is required, and the danger of the subsynchronous reactance are present, because you are inserting the capacitor essentially that may lead to reduce the value of the impedance, and if it is insertion is slow, that leads to the subsynchronous impedance, and ultimately you got a delay at least actually one of cycle. So, thus it is not advisable to use only the TCSC as a series compensator. It can be combinations of the GCSC TCSC, it can be combination of the TSSC, which we have discussed, that is a versatile device. With that it can be coupled. So, since it is thyristors, its control has got lot of limitation, but this TCSC could be applied for the power flow control and for damping power oscillation where required speed response is moderate. So, this is the where it can find its application. You see, this is the Vc max, the maximum Vc can be applied, and this is the IV characteristics, and accordingly this value can be changed. This is I max and this is I mean. Within the range you can operate, you can choose any value of the admittance. The basic VI characteristics of the SSC with the 4 series connected compensator module operate to control the compensating voltage has been shown this figure. For this compensation, the mode of reactance of the capacitor bank is chosen as to produce on the average rated compensating voltage, that is this value. Vc max is basically 4 Xc into I mean. So, what happened then? As a result, when I mean is increased towards I max, so losses will increase definitely, the capacitor banks are progressively bypassed by the thyristor valve to reduce the overall capacitance and in a spike like manner. So, you had for this reason you have this kind of spikes in admittance, thereby maintain the compensation voltage with increase in current limit. Since you are changing the impedance of the line, current limit may touch, and thus also the loss. So, ultimately you will have this kind of thing. This is the way it will change, and this is the case of Vc equal to 0, and thus you have bypass all the thyristors, all the capacitor, and thus thyristor is switched, the thyristor losses will account, and current, if current is more, this will increase in a parabolic manner. The loss present of the rated valve output versus line current characteristics of the SSC operated in the voltage compensating mode. So, this is there. For 0 voltage injection, all capacitors are bypassed, and for maintaining maximum rated voltage injection, capacitor are progressively bypassed. So, ultimately one after another capacitor can be bypassed. So, let us see that impedance compensation mode. So, this is basically x, this is I and this is V, and this is actually the maximum curve, and ultimately TSSC has to operate in this zone. In this, capacitive impedance is chosen so as to provide maximum series compensation at rated current for Xc equal to Vc max by I max. The loss versus line current characteristics for this compensation mode for the 0 compensating impedance, all capacitor banks are bypassed by the thyristor valve. For maximum compensating impedance, all thyristor valves are off, all capacitors are inserted. So, this is the losses, this is for x equal to 0, we will have maximum losses gradually when it is bypassed. So, switching losses will come down gradually. The maximum rated current and corresponding capacitor voltage are designed value for which the thyristor valve and the capacitor banks are rated to meet the specific application requirement. So, we have to choose properly the DC capacitor voltage and the value of the capacitor. Constraint imposed by the physical device limitations on turn on condition of the thyristors, such as DIDT protections and the surge current magnitude, would necessitate in practice to use a current limiting reactor. For this, it is not only capacitor, there will be a current limiting device that will give you DIDT protection in series with the TCSC valve to handle the bypass operation, because if the capacitor is discharged with the thyristors, high current will flow through the thyristors with high DIDT, that may damage the thyristor. If reactor in series valve is included in the TCSC structure, then the resulting power circuits offer new control operation which significantly improve the operation and the performance characteristics of the series compensator. So, we have, it is advisable to put a series reactor with TSSC. So, for this reason, this become the actual circuits. Mainly this purpose is to limit the DIDT across this thyristor. This thyristor is controlled series capacitor. So, it is a improved version of the previous version of TSSC. The thyristor controlled series capacitor TCSC scheme consists of the series compensating capacitor shunted by the thyristor control reactor. So, you will have a inductor here. In practical TCSC implementation, several such basic compensator may be connected in series to obtain the desired voltage rating and the operating characteristics. So, it can be actually put into the modular form in series. This arrangement is similar structure of the TSSC that we have discussed here, and if the impedance of the reactor XL is sufficiently smaller than that of the XC, it can be operated in on off manner like previously discussed TSSC. Now, so what will be its reactance? The TCSC is used to provide a continuously variable capacitor by means of partially cancelling the effective compensating capacitance by TCR. TCR is a continuously variable reactive impedance controlled by the delay angle alpha. The steady state impedance of the TCSC is a parallel LC circuits consisting of a fixed impedance XC and a variable impedance XL. So, overall impedance is given by, it will be controlled by alpha XC XL alpha XL minus XC. So, that gives you XL alpha equal to XL by pi minus 2 alpha minus sin alpha. Alpha is the delay angle measured to the crest of the capacitor. So, this is the expression where actually you can compute the amount of the XL, and accordingly you can compute the firing angle of the thyristor. Please note that this has to be solved since there is a alpha and sin alpha. So, this equation has to be solved by the iterative method. So, what are the actually characteristics of the TCSC? We can say how to calculate alpha. The impedance of the controlled reactor XL alpha is varied from its maximum to the infinity towards minimum XL. The TCSC increases its minimum capacitive impedance, that is TCSC minimum equal to XC equal to 1 by omega c until the parallel resonance at XC equal to XL alpha, and theoretically it becomes infinite. So, thus it can offer a huge impedance. Decreasing XL, sorry, it should be suffix alpha by varying the triggering angle, the impedance of the TCSC, that is X TCSC alpha, becomes inductive, and reaching maximum value for XL into XC by, that is a combination of it, XL minus XC at alpha equal to 0. Therefore, with the usual TCSC arrangement in which the impedance of the TCR, that is XL, is smaller than the capacitor XC, otherwise this condition may prevail and you will offer actually infinite impedance, and thus no current will flow through the transmission network. So, TCSC has two operating ranges around the internal circuit resonance, that means the capacitive mode and the inductive mode. So, we should have both the mode possible, and that flexibility is given here. And this mode is inductive mode, you can change with the alpha, and here is the region where you can change alpha angle, actually triggering angle. So, it is equal to 0 to minimum alpha. Similarly, the C limit will change alpha C limit will change accordingly. So, when it will be capacitive? There is a two mode of operation in TCSC. The alpha varying from IC alpha minimum or limit to pi by 2 with respect to the peak of the capacitor voltage. Similarly, you will have an inductive alpha for alpha varying actually from the 0 crossing of the voltage 0 to alpha minimum with respect to the peak of the DC capacitor voltage. Thus, this is the characteristics in the inductive characteristics. This can change to alpha 0 to alpha minimum, and here it can change to alpha to pi by 2. So, this is the actually the alpha value you can choose as for the capacitive. If you wish to have a capacitive region, you have to restrict alpha with this region. If you wish to operate in inductive region to increase the inductance of the circuit, you have to choose this alpha. So, let us see that VI characteristic, we have actually the waveforms of the TCSC. Let us assume that the thyristor valve is initially open. So, all the current was passing through the capacitor, and that is what happened, and the prevailing line current produces the voltage Vc 0 across the fixed compensated capacitor. So, across this device. Now, we shall trigger it. Suppose that the TCS is to be turned on at a measured from the negative peak voltage of the DC capacitor. So, this is the value of the DC capacitor and this is the delay angle alpha. At this instant on turn on, the capacitor voltage is negative, and also you can see that line current going to be positive, and thus charging the capacitor in opposite direction. So, it will charge the capacitor because polarity, this current you can take it a positive polarity. So, ultimately you got this. So, in that moment you have fired the thyristor, and thus it will actually charge the capacitor in opposite direction. During the first half cycle, in a similar subsequent half cycle of the TCR operation. So, what is the advantage of it? So, see that what happened here. So, this is the Vc, all of a sudden there will be a sudden jump. Now, from there you get an alpha. So, here thyristor has been triggered. So, it will be jumping out to the minus Vc2 by actually some voltage of negative voltage to the same magnitude of the positive voltage. At this instant, the closing switch SW to subsequently independent event will take place. So, this transient has to be controlled. So, we have to understand this actually the voltage current characteristics of this thyristors. One is that the line current being a constant current source continues to charge or discharge depending on a different cycle of the capacitor. The other is that the charge of the capacitor will be reverse during the resonant half cycle of the LC circuit from the switching or the switch closing. So, it will be jumping out from this point to this point, and thus what happened? The resonant charge reversal produces a DC offset for the positive half cycle and the half cycle of the capacitor voltage. So, you will have a DC component comes into the picture. So, this is the overall characteristic, let us see. So, this is the VCO alpha that would have been here without the triggering. Once you trigger, what happened, actually this is the Vc alpha. So, since it has got a DC offset, it will shift like this, then it from here it will be actually go like this, and you will have this kind of characteristics. Huge DC swing will be there. Let us understand this graph. The subsequent negative half cycle, the DC offset can be observed by the magnitude of same angle alpha. Let us see that. Thus, the voltage waveform symmetrical to the 0 axis can be produced. The relevant current and the voltage waveform of TCSC operation in the capacitive regions is shown. So, this is the alpha and this is the conduction angle sigma. See that, and this is basically this voltage across the switch, and so this is the switch and I alpha. Similarly, for the inductive operation, this is the lower one, upper one is the capacitive operation, where where the overall impedance is inductive, we will see its characteristics and we will see that switching pattern. So, what happened, this is actually Vi and this is actually Vc alpha, and this sinusoidal voltage is Vc 0 and this one is your Vc alpha. So, we will have this kind of pattern, and thus what happened of the switching. So, you will find that till angle triggered alpha, it will follow the same, since it is connected parallel to the DC capacitor, connected to the capacitor. So, it will have follow the same voltage pattern, then it is triggered, ultimately you will find I alpha and the voltage will be 0. Then thereafter what will happen here, since there is no current, you will find current is 0 and you will have the thyristor voltage, Vc switch will be the same as the DC bus voltage, and thereafter again it is been triggered, and thus what happen, you will have a current will flow same as the here. So, accordingly it is a superimposition of the ISW and IL in the same waveform, and this is the zone of operation of the inductive operation of the TCSC. Now, what we can conclude from these graphs? The time duration of the voltage reversal is depending on this actually this ratio XL by XC, but also on the magnitude of the line current. That is XL is smaller than the capacitor XC, then the reversal is almost instantaneous. The periodic voltage reversal produces a square wave across the capacitor that is added to the sine wave produced by the line current. So, you may have this kind of TCR, and ultimately you can think of Vc alpha is equal to Vco plus TCR. So, what happened? There will be a square wave and it is superimposed by a sinusoidal wave. So, thus you get this kind of characteristics. The steady state compensating voltage across this series capacitor comprises an uncontrolled sinusoidal wave and the controlled component of the square wave. So, this is the Vco and that is uncontrolled, and this is actually VCTCR that is controlled. So, this imposition makes it actually Vc alpha. So, what we can say more about the TCSC? So, square wave magnitude is controlled through the charge reversal by TCR. For relatively small XL, the time duration of the charge reversal is not instantaneous, so it will take some time. But it is quite well defined by the natural frequency of oscillation, where f is basically 1 by under root of omega c. So, omega c is under root of L c for the TCSC circuit. Since the TCR conduction time is approximately equal to the half period corresponds to this frequency, that is T by 2 equal to 1 by f. So, we can choose the value of the XL. The value of the XL is increased related to the XC, and the conduction period of the TCR increases, and what happens then? The zero crossing of the capacitor voltage become increasingly dependent on the prevailing line current. So, this is the actually the consideration. Okay. Thank you for your attention. We shall continue with the TCSC in our next class, and we shall try to complete our all the series regulators in our next class discussion. Thank you for your attention. Thank you.